I'm going to talk about sort of a culmination of papers with Kenny Ascher and Yuchen Liu. And if you have any questions, please feel free to unmute yourself and ask. Happy to talk more after the talk as well. I also have not used Teams very much before, so if something happens, technologically, difficulty, something, please let me know and we'll try to get back on track with the screen share and the sound and whatever happens. So hopefully I can tell a little bit of a story about K3 surfaces and using K-Moduli, which is a sort of recent advance in algebraic geometry, to get a complete picture of a really nice story, really nice compactification of different moduli spaces of K3 surfaces. And so, possibly an informal motivation that I think many people here are probably aware of. If you're studying moduli of varieties and you place different stability conditions on the variety, you can end up with different moduli spaces. This is intentionally informal. And we see this for curves. And generally, I'm going to be talking about compact moduli spaces. But even for curves, we have the smooth locus, MG, smooth genus G curves. G is at least 2. And probably for safety, I should say that everything here is happening over C in this talk. If you have questions about beyond C, let me know. But this is the comfort zone. And all of our smooth genus G curves, they're the standard compactification MG bar of Deligne-Mumford stable curves. Which are curves with ample canonical that have possibly at worst nodes as singularities. So this is some stability condition we place on the objects we're parameterizing. And what is a really nice story that has been studied by many different people is that this isn't the only option. So I could also consider a compactification, sometimes called pseudo-stable. I think these are originally due maybe to Schubert, pseudo-stable curves, which means we put a slightly different stability condition on the curve, but roughly the idea is that we allow at worst cusps. And part of the story between these two moduli spaces is that there's actually, in this case, an actual morphism between the spaces, and it has a very nice modular interpretation given on a family of curves. If you have a family of Deligne-Mumford stable curves, you can make this morphism by contracting any elliptic tails in the fibers. And a contraction of an elliptic curve will give rise to this cusp here. So there's actually more stability conditions, and this idea of the log minimal model program on MG bar gives this very beautiful picture of different families of curves that we can talk about. But there are many ways to view these different stability conditions on curves, and the one will, less so for curves, but one that we'll really be focusing on today, specifically for higher dimensions and K3 surfaces, but moduli spaces of varieties coming from the viewpoint of K stability. And K stability is a differential geometric notion that has recently been studied and really generalized to the algebraic geometric setting. And I guess maybe I can call this a recap. Not that everyone should know this already, but the main theorem is that K stability is the right stability condition this is a value judgment, so you may disagree, which you're welcome to construct moduli, or at least a well-behaved moduli space of log Fano or just Fano varieties. And so this is really the content of something called the K-Moduli Conjecture, which has been recently just proven in generality, but perhaps I will give a weaker version of the statement to say what I mean here. So this is a theorem of Li, Wang, and Xu, K-stability being the right notion to construct moduli spaces of log Fano or Fano varieties, is that there is a nice moduli stack or a good moduli space so just a nicely behaved parameter space that parameterizes smoothable K semi-stable, or if you're looking at the moduli space, K polystable Fano varieties with fixed volume and dimension. This is a older result, and I mean the new result essentially gets rid of the word smoothable there and is due to many people, but this is where we'll start here. And to give you just an idea what this K semi-stable condition is, it looks, perhaps if you're more familiar with it, algebraically similar to the conditions you put on varieties when you're talking about GIT. And by that I mean in GIT you look at these one parameter subgroups, so essentially some one parameter family of a variety, and you look at the Hilbert-Mumford weight and you ask for this to be positive or negative or greater than or equal to 0 to be K semi-stable, or excuse me, GIT stable or GIT semi-stable. And with K stability, you look at a very similar picture, but instead of a one parameter subgroup, you have something called a test configuration. But it is still just a one parameter family of your object in question over A1. And you still have a weight associated to that test configuration called the Futaki invariant. And you ask for this to be positive or greater than or equal to 0. So algebraically, it's quite similar. It's maybe part of the crucial difference is that in GIT, you're requiring your action, your one parameter family, to live inside a fixed projective space, inside your fixed Hilbert scheme. And in K stability, you're not fixing the ambient space. But in any case, to give you at least a feel of what this might look like, this is a very sort of cheating way to give you an intuition for K stability without actually defining it. But today the talk is supposed to be about K3 surfaces, so you might be reading this and say, well, it's about Fano varieties, which are not K3. K3 surfaces are not Fano varieties. And the key is that instead of just making moduli spaces for Fano varieties, we can use K stability to also make moduli spaces, compact moduli spaces for log Fano pairs. So again, this result will also generalize to the non-smoothable setting, but this, as stated, I'll just give it a, just keep it in case we'll use it today. Together with Kenny and Yuchen, we proved that part one, you can do the same result as the Li, Wang, Xu theorem, saying there's an Artin stack, or respectively a projective good moduli space that parameterizes K semi-stable log Fano or polystable log Fano pairs satisfying a few conditions. Oops, I should put this. I'm not claiming that our result is the one that generalizes to the non-smoothable setting. There's a lot of hard work that goes into that with many people. So we'll put smoothable log Fano pairs, xd, or maybe x alpha d. We can vary the coefficient with a fixed Hilbert polynomial and x is a Fano variety. The divisor d is a rational multiple of the anti-canonical divisor. So this is Q equivalence. And alpha is some coefficient that can range from 0 to possibly up to 1, but depending on what this coefficient r is, it might not be able to get all the way up to 1 and stay log Fano. So we can make a moduli space of pairs that satisfy these conditions. And part 2 of this result is that these moduli spaces admit a wall crossing framework. So this alpha in front of the divisor, the coefficient of the divisor, allows us to make actually many different moduli spaces. So, just for context of the next result, if I define, or I call this moduli space mk alpha, k for k-stability, alpha for the coefficient of the divisor, these moduli spaces admit a natural wall crossing framework. When we vary alpha. And so by that, I mean, maybe the usual picture for wall crossings, there's rational numbers, alpha 1 up through alpha n, which is the max alpha could possibly be, such that we have, as long as alpha, maybe alpha and alpha prime are in the same interval between these walls, we get the same moduli space. Or the same moduli stack. And at the walls, we have a particular diagram that has a precise structure. It has some precise structure of a local VGIT framework. So maybe without writing that down, I'll just leave it sort of at that. There's, and one expects that, at least on the level of moduli spaces, there's a nice birational transformation that goes between these different moduli spaces. So it may be a blip, divisorial contraction, something like that. So maybe just a general remark before getting to how all of this relates to K3 surfaces. As we vary alpha, the key observation perhaps is that we're getting possibly different pairs. So a theorem of Vodaka says that if I have a K semi-stable log Fano pair, then in the world of singularities, or the classic MMP type world, the pair X alpha D has to be KLT. And this gives at least some idea of how these moduli spaces could depend on alpha, because if alpha is quite small, the divisor D could be quite singular. It could be, I mean, everywhere non-reduced. But when alpha is large, in order for XD to be a KLT, D can only be mildly singular. So we have a maybe motivation, or the picture to keep in mind is that we can make these different moduli spaces that depend on alpha, and as alpha increases, we're going to have to do birational transformations to these moduli spaces to replace the pairs where the divisor is too singular by a pair where a divisor is less singular. So maybe that's the setup, but the goal is to talk about how all of this relates to K3 surfaces. Because the K3 surface is not a log Fano pair, but the spoiler is that the K3 surfaces we're going to talk about, in this case quartic K3s, we can embed all of them into up to, there's, I guess, 4 different Fano threefolds and do moduli of those pairs, where the ambient space is a Fano threefold and S is the surface, and we can make K-Moduli spaces of those pairs. So K3 surface, at least for the purposes of what I'm going to say, is a projective surface, potentially mildly singular. So I guess we could say with Duval singularities, such that the canonical bundle is trivial and H1 of O is 0. And in this, I guess we'll also be talking about the structure of polarized K3 to get the idea of a degree. So a polarized K3 surface is a pair SL, where S is a K3 and L is an ample line bundle. On S, and we'll refer to the degree of a polarized K3 is the degree of L. So sometimes this is written as 2D because it happens to be even, but I'll just use D. And it's also, I guess, intrinsically in this way we can define the genus, which is 2G minus 2. And these numbers are relevant because there's a structure theorem for K3 surfaces of this form. So, or I mean, depending on these numbers. So this is, I think, originally due to Meyer, and it says, if I consider the this line bundle L, it defines a map from S to PG, where G is that same G in the genus in the definition above, and there are 3 possibilities for this map. The generic case, if D is at least 4, this is the generic case at least, this map is birational. Onto a normal surface of degree D. The hyperelliptic case, in which case maybe the name is suggestive, hyperelliptic, as in a hyperelliptic, similar to what we would see in a hyperelliptic curve, the map is a 2-to-1 as a finite cover of its image, and it's 2-to-1 onto a normal surface of degree D over 2. And the general member of the linear system L is hyperelliptic, so the name coincides with many ways. And then there's a third case, the unigonal case, in which case the image of this map is a rational curve of degree G. And the fibers of the map just from S to its image, or as the general fiber is an elliptic curve. So we have these 3 possibilities, and essentially they behave quite differently, and the different geometry of the different cases really will be the key in defining these K-moduli spaces. But perhaps to give a toy example before we talk about quartic K3s, the first example that we could encounter and even study with the wall crossing framework of K3s or of K-moduli is in the degree 2 case. So in the degree 2 case, our linear system here gives a map to P2, and this is necessarily not birational. And so the generic surface, K3 surface of degree 2, is one of these hyperelliptic K3s. So the generic case is when this is 2 to 1, and the image happens to be, based on computation one could do, the image just branched over a sextic curve. And so if one wanted to set up a moduli problem to study K3 surfaces of degree 2, we could study the moduli of the sextic curves. Perhaps with coefficient 1/2, so that we're branching correctly. But the benefit of the K-moduli picture is that we can vary the coefficient in front of the curve and study moduli of these pairs using K-stability. So in my first work with Kenny and Yuchen, we study moduli of plane curves from the viewpoint of K-stability, and we can define a few different moduli spaces. You could look at the GIT moduli space of degree 6 curves. So this would be a curve of degree 6 in P2 that is maybe GIT semi-stable. I'm writing this set theoretically, which maybe doesn't make a lot of sense, but the points of this moduli space are the, I'm also being a little bit sloppy about space versus stack, but in any case, we could define the GIT moduli space, and we show that this GIT moduli space, perhaps from the point of view that I was describing earlier about K-stability looking very similar to GIT, happens to be a K-moduli space. And in fact, as long as the coefficient of the curve is sufficiently small, this GIT moduli space is the same as the K-moduli space, where this K-moduli space is parameterizing K semi-stable or perhaps polystable if I'm really talking about the moduli space, pairs X alpha C, where X is a degeneration of P2. And C is a curve in the appropriate anti-canonical linear system. And we can use K-moduli wall crossings to interpolate or at least increase alpha between the GIT moduli space and the moduli of pairs, P2 with coefficient 1/c, and there's a natural compactification of this, which maybe I won't go into, that really is the Baily-Borel compactification of these degree 2 K3 surfaces. So it's a very short interpolation. You have the Baily-Borel compactification of moduli spaces of the K3 surfaces. You have the GIT moduli space of the plane curves of degree 6. This happens to be a K-moduli space as long as alpha is between 0 and 1/4. And when alpha is 1/4, you do have a wall crossing in terms of the moduli spaces. And if I'm just talking about the moduli spaces, I guess I could put less than or equal to here if I'm not talking about the stacks. And after you cross the wall at 1/4, we get a different K-moduli space as alpha ranges from 1/4 to 1/2. And I've only defined K-moduli spaces of log Fano pairs. So based on the definitions that I've given so far, it doesn't exactly make sense to say this is the moduli space of the K-moduli space of pairs 1/2, because the pairs P2 1/2 C aren't log Fano anymore, but if you extend the definitions a bit, you could make sense of this. And this completely interpolates between the GIT moduli space and the Baily-Borel moduli space. And both of these maps have explicit descriptions. So the first wall crossing phi is a Kerr-1 partial desingularization of a particular point in the GIT moduli space, which is a triple conic. So if you take a conic, that's a degree 2 plane curve. If I cube it, I get a degree 3 plane curve. Or sorry, if I cube it, I get a degree 6 plane curve. And by blowing up that point, we can think about this is a desingularization of the moduli space. This is a sort of uniquely bad singular point of the moduli space. But you can think of this as another way. So the conic, if we think about the structure theorem, I'm going to scroll up temporarily, for K3s, degree 2 K3, a unigonal degree 2 K3, the image is a rational curve of degree 2. So this morphism, where we're blowing up this sextic curve, if you think about these as families of K3 surfaces, when you blow up a point, you extract a divisor. It extracts the divisor parameterizing the unigonal degree 2 K3s. And the map, this map C also has a very explicit description. You could think of it as the ample model of the Hodge bundle on the K-Moduli space. So up here, there's a Hodge bundle, and you can take the ample model to get the Baily-Borel compactification. You can also think of it as a Q factorialization if you think in the other direction. We do have this divisor in the Baily-Borel moduli space parameterizing the unigonal K3s. And this map, if you think of that divisor living in the Baily-Borel moduli space, this map is the Q factorialization of that divisor. So this picture of these three moduli spaces was studied before our application of K-stability, and the same picture was attained also by Shaw and Loenga. And without the viewpoint of K-stability, you can define these moduli spaces in another way, but sort of a nice observation is that K-stability provides an alternate perspective, and it provides a nice alternate perspective of constructing these moduli spaces and the maps between them that will generalize nicely to the degree 4 case. So with this idea in mind, we can ask ourselves what happens for quartic K3s in the next case. And maybe the goal would be to have a similar picture. We have the Baily-Borel moduli space of quartic K3s. We have many other moduli spaces. We have, in this case, not a GIT moduli space of plane curves, but we have a GIT moduli space because they're quartic surfaces in P3. And we could ask ourselves how one can interpolate between these two moduli spaces. And in fact, you can use K-stability to do so. And many of the results are quite similar. I mean, there'll be a map on the end that's a Q factorialization of certain divisors, and the first morphism will be extracting one of the divisors and so on. So a lot of the picture will look quite similar, even though here we're parameterizing curves, the branch locus, and degree 2 K3s, but maybe that toy example is good to keep in mind. So in the degree 4 case, if I'm looking at degree 4 K3s, my ample line bundle gives me a mapped P3, and there are three choices. The generic case is an embedding as a quartic surface. The hyperelliptic case is when this map is 2 to 1 onto its image. and the image is a rational surface of degree 2. Fortunately for us, in P3, we know what those are. So we either will have P1 cross P1, or the singular quadric cone, which I'll use, I guess, the weighted projective space notation, P112. Or the final case, the unigonal case, the image of this map is a twisted cubic in P3, and the fibers are elliptic curves. So from this perspective, we have at least 2 natural moduli spaces we could come up with, or at least compact moduli spaces. And there's the GIT moduli space. So I guess I could write something more detailed than what we wrote before with plane curves. Look at the space of quartic surfaces, and we're just going to essentially look at the GIT stable or semi-stable locus and quotient by the automorphous subgroup and make a good quotient here. Maybe I'll just use the same notation and call this MGIT. So these will be surfaces S that are GIT semi-stable or polystable if we're talking about the moduli space. And we also have the Baily-Borel compactification coming from Hodge theory, and the global Torelli theorem, which embeds the quartic surface into the period domain. Maybe I'll call D mod gamma or something. Oh, if I could spell period, there we go. And we get a compactification, which we'll call, again, F star. And from the global Torelli theorem, the generic surface in the GIT moduli space does have Duval singularities. So these two are certainly birational, and usually perhaps one would consider the map going in the other direction. So usually maybe one would think of a generic birational map going from the GIT moduli space to the Baily-Borel space. But in this case, in the case of K-stability, maybe I'll think of the map going this way. And what it turns out is that we can analyze the birational geometry of this map inside of the Baily-Borel compactification. There's this locus M0 of our usual quartic surfaces with AD singularities or Duval singularities. And those all happen to be GIT semi-stable. So this lives inside both of them. But some of the differences here in the GIT moduli space, the complement of this locus parameterizing the good quartic K3 surfaces is small. So I guess the dimension of, or sorry, not the dimension, the codimension of the complement is at least 2. On the other hand, in the Baily-Borel moduli space, the complement is larger. This happens to have codimension 1, and there's 2 divisors in F star that get contracted in the GIT. So in fact, the hyperelliptic K3s and the unigonal K3s each form a divisor inside the moduli space, and these both get contracted in this rational map to the GIT moduli space. So this gives maybe some hints on if we want to try to understand this birational, or excuse me, this rational map between the Baily-Borel moduli space and the GIT moduli space. Depending on which way you're thinking the map going, forwards or backwards, we have to either start at the GIT moduli space and extract these divisors and do maybe other wall crossings to glue them together in the right way before going to the Baily-Borel space, or vice versa. We need to start here, maybe perform some birational transformations before we can contract them to get the GIT moduli space. And indeed, I mean, this is exactly what one can do. So this is perhaps the main result in the talk, and to not give you a bunch of different fractions, I will say we can interpolate between these moduli spaces, f star to mgit, via a sequence of explicit K-moduli wall crossings. And there are 10 different wall crossings. There are 1 that extracts the hyperelliptic locus, then 8 that do some flips inside the hyperelliptic locus, and then 1 that extracts the unigonal locus. So there's quite a few, so I won't try to write them down all. But the key of this picture is that the picture looks very similar to the degree 2 case. And by that I mean we have the GIT moduli space of quartic surfaces, and that happens to coincide with the K-moduli space of pairs. So this is the space of pairs, P3 S, alpha S, when alpha is sufficiently small. And we have the Baily-Borel moduli space, which if you, again, I didn't define what it meant to be a K-moduli space of log-Falabiau pairs, but for many intents, this could be considered the K-moduli space when the coefficient is 1. And there's a sequence of explicit K-moduli spaces here and here, where we can write down exactly what happens in between. And just as in the degree 2 case, this last map is the ample model of the Hodge bundle on the K-moduli space, the very last K-moduli space. And, or you could also view this as this map is the Q factorialization of both, actually individually, this map drops Picard rank by 2, Q factorialization of these divisors HH and HU, parameterizing the hyperelliptic and unigonal K3 locus. So for the sake of time, I won't write down explicitly all of the walls, but I do want to give a little bit of an idea of how this is proven and how K-stability comes in, where the log Fano pairs come in, and how this relates to some previous work by various others. So I guess the key ways to think, the key tools are involved here are part 1. K-moduli is the study of log Fano pairs. So we need to study essentially Fano threefolds. X alpha S, so X is going to be a Fano threefold, a singular Fano threefold in general. It turns out they're all very mildly singular. They're all Gorenstein canonical threefolds, and S is our K3. Oops. So sort of step one, which in practice actually comes from studying the wall crossings to determine what all these threefolds are, is to embed all of the surfaces into a Fano threefold. And then one also will have to study the birational geometry of those threefolds to understand their deformations, to make sure we've got them all, to make sure they're K-semi-stable, and so on and so forth. But one has to construct the threefold. And it turns out in this setting, one can show there's not very many choices for X. X is either P3, the generic quartic surface is embeddable on P3, or it's the cone over the quadric surface with respect to the degree 2 embedding here, or it's the cone over the singular quadric surface with respect to the degree 2 embedding, and oops, sorry, the 4 doesn't come in yet. Where by O2, I mean O2 on P3 restricted to these surfaces. Or there's one final surface, which I'll just call XU, which is a Gorenstein canonical, or sorry, one final threefold, Gorenstein canonical threefold containing the unigonal K3s. So in this setting, I guess part of the reason that one can actually explicitly study all of the K-moduli spaces and show that there's all the pairs we want to be are K-semi-stable and the ones we don't want to be aren't is because there's not very many choices for the threefold. It's just one of these 4 things. And then really to prove the result, the hyperelliptic locus and the unigonal locus are quite different. They behave quite differently. The hyperelliptic K3s all embed inside these cones, which is maybe clear. It's a 2-to-1 cover of P1 cross P1 or P1, 1, 2. So we're just taking the natural cover that we could get there. And so the key when you're studying the wall crossings is to study the hyperelliptic and the unigonal loci separately. And it turns out that until the very, very last wall, these 2 divisors are disjoint. So until this last wall that kind of contracts some small stuff into F star, these divisors are disjoint. And so studying them separately works perfectly. And I think perhaps maybe surprisingly, the unigonal case is much easier. There's only one wall, it just extracts the unigonal divisor, and that's all you have to do. The hyperelliptic locus, which perhaps seems like we understand better, they're just covers of P1 cross P1 or P1, 1, 2, actually requires quite a bit more work. And so the hyperelliptic K3 is the key to study these wall crossing is in fact just like the degree 2 case, and study K-moduli of, in this case, well, what it turns out is that if I consider my degree 4 case, it's 2-to-1 onto a quadric surface. If the quadric surface is P1 cross P1, then the branch locus is a 4-4 curve. Similarly, if Q is P1, 1, 2, it happens to be the if you think of that as singular quadric, it's still a 2-4 complete intersection. So I guess the point is the branch locus in either case is always a 2-4 complete intersection in P3. And so we can study moduli of pairs for the hyperelliptic quartic K3s. We can consider moduli of pairs I mean, really moduli of these 2,4 complete intersections, but moduli of pairs P1 cross P1 with a 4,4 curve, or P112 with I guess it's a degree 8 curve in the weighted coordinates, P1, 1, and 2. So we can study moduli of these pairs, and then you can do exactly what is done in the plane curve case, and consider just the Baily-Borel moduli space for hyperelliptic K3s. It turns out that this is well defined, and the GIT moduli space. These curves on the singular quadric are all degenerations of these curves on the smooth quadric, so we can consider the GIT moduli space of just the GIT curve, semi-stable curves on P1 cross P1. Oops, maybe I should write this as this way. So C is a 4,4 curve, and it's GIT semi-stable. And we can interpolate between these moduli spaces, just like we are trying to do in the general case, but it turns out this is somehow easier to do when we're talking about curves on P1 cross P1 than in the general cases. And we can interpolate between these using K-stability. And as it turns out, all the hard work has already been done. And I guess maybe I'll put a comment first and then a theorem. So Laza and O'Grady study this exact problem of interpolating between the hyperelliptic quartic K3s and the GIT of curves on P1 cross P1. And Laza and O'Grady study this using VGIT. So defining an appropriate line bundle on this parameter space of these complete intersections, and varying it as you go through, and determine all of the wall crossings. And as it turns out, in this case, there's a very special case. This is not true in general if you're not talking about 4,4 curves, but in the case of 4,4 curves, the K-moduli walls and the K-moduli spaces and wall crossings and stacks, I mean, are exactly the same as the VGIT moduli spaces or wall crossings that Laza and O'Grady define. So we show that the K-moduli has to coincide with the VGIT, and then we can use their result to explicitly write down all of the wall crossings. So this is false. When C is not a 4,4 curve. So this is very special to just the case we're talking about in this case. But in any case, to wrap up here, once we have the wall crossings for the hyperelliptic K3s, we can now use this to construct all of the pictures for quartics in general. So we start at the GIT moduli space, and then step 1, we extract. So that's our starting point. It happens to be a K-moduli space when the coefficient is sufficiently small. We extract a divisor that parameterizes hyperelliptic K3s. This is the first wall. We use the wall crossings of Laza and O'Grady in the hyperelliptic case to find all walls I'll put this in quotes, intersecting this locus. And so what I mean by that, when you go to cross the wall, there's some locus in the moduli space that destabilizes, that results in the need for a wall crossing at that point. And if that locus that destabilizes intersects this hyperelliptic divisor, then we can use the description of the wall crossings above to figure out what coefficient that would have to occur at and what curves would have to be replaced, and then take appropriate double covers to figure out what surfaces have to be replaced. And then the very last piece is to study the unigonal walls separately, but there's only one. So it doesn't take much more work. And then the result is an explicit description of the map going from the Baily-Borel moduli space to the GIT moduli space of quartic surfaces and all of the intermediate wall crossings. So K-stability provides us with the full picture, and there's obviously maybe a lot that I haven't said of how you actually check any of these things are K-stable or K-semi-stable and what works, but it's a really beautiful study in birational geometry of the Fano threefolds for a lot of the details that are hidden here. But I'll stop here, and if anyone has any questions, I'm happy to answer, or I can elaborate on anything that I have said. Thank you very much for your attention.